curves. Please start.
Okay, thank you very much. Thank you very much for the invitation. I'm enjoying the conference a lot, and it would better go there in person, but like it's difficult. And yeah, thank you very much for this opportunity also. So today what I want to talk about is how to study the structure of Selmer groups of elliptic curves. So E over Q is always on elliptic curve. And of course, the leading problem of the arithmetic of the elliptic curve is Burson-Singleton-Dyer conjecture. And rather than stating BSD again, so let me loosely write down the connection. So the connection between the behavior of the complex L function of elliptic curve around S equals 1 or complex L function of E around S equals 1 and the arithmetic of E itself, which means the size of model wave group, the rank, for example, and the size of the Tay-Shafrovich group. And these are what we are interested in, and Burson-Singleton-Dyer conjecture make the connection. And here the behavior means, of course, the first one is the vanishing order at S equals 1. And the second is, of course, the leading term. And by the way, if you have any questions, just stop me. And recently, there are really like a significant development towards the Burson-Singleton-Dyer conjecture. And in fact, many heroes on these results already in this room, online or offline both. So for the first year, let me, I will write down some names, but like I try to keep all the names as much as possible. Starting from the Grosjean Kolyvagin. And first, so rather than like stating all the results, let me just write one sentence. So if the vanishing order is smaller than or equal to 1, we know many of them, many parts of the Burson-Singleton-Dyer conjecture. Then we know many parts of BSD. And let me just put some names. The Karubin, Kazacaro, and the work of Skinner-Urban. And there are so many names appear. There's like Sinwan and Kobayashi and Jacep-Skinner-1. All results are like towards the vanishing order of the rank part and the leading term part both. There's like one and Francisco Castilla and Burungale Tian. Sorry, it's the Burungale Tian, and also like a Buyok Sasaki Pollock. And yeah, name goes further, and also we know many parts of the P converse. Means if the Selmer rank is 1, sometimes Selmer rank is 1 implies the analytic rank is 1. And sometimes we need to assume the the finiteness of the P part of the T-Sharp-Leibniz group. And this start with a Skinner, Wei Zhang. Carl Rubin also made this, and Burungale Tian. And I also made a small result, and yeah, then Burungale Skinner Tian also, yeah, should be here. And it develops further in many. It has the many generalization, and these are kind of what we know about the arithmetical elliptic curves. And I think tomorrow Chris Skinner's talk will talk more on the advance. And today my focus is slightly different. And so let me first recall the fundamental exact sequence, which make the connection between the model way, Selmer, and Shah. And let me fix the prime P. By the way, I'm sorry about that. Sometimes my daughter shouts, and you may heard that. I'm sorry about that. Okay, so elliptic model way group tensor QP mod ZP goes to Selmer group of elliptic curve, and P part, which is a Galois module, and the P part of T-Sharp-Leibniz group. And in fact, when we use the Euler systems in Iwasawa theory, we mainly focus on the Selmer groups, not Modelway or Shah themselves. So that's my Euler systems and Iwasawa theory. And today's focus is how to go beyond the Burch-Simpson diagonal conjecture in some sense. How to go beyond PSD. What do I mean? So the first one is I want to focus on the structure of Selmer groups, not just size. And in terms of comparing with the known results, I would like to say something without any restriction on the rank. So let me give some example. The first example is in fact due to Prasad Shaka. And the computation is in fact done by Masato Kurihara. And this elliptic curve has the LMFDB index. LMFDB index is 423801.ci1, and P is fixed by 5, and it's on rank-zero elliptic curve. I'm sorry, it's the rank-zero elliptic curve. So, and the L value divided by the Néron period, in fact, the 10,000. This is 2 to the 4 times 5 to the 4. And it turns out that 2 to the 4 is a Tamagawa factor. So this 5 to the 4 contribute the 5 part of the T-Sharp-Leibniz group. And the question is follows. So E over Q and 5 part is Zima 25 Z, the 2 copy of that, or Zima 5Z is 4 copy of that. That's the first question. And this question itself already goes beyond the Burch-Simpson diagonal conjecture. And we will see the answer is the this one, not this one. And the second example, let me just write down here. Example 2 is the LMFDB 5077.A1, which is the rank 3 elliptic curves with the smallest conductor. Is 5. And we know this. And with smallest conductor. And can you say about the 5 part of the tail-shaped scope of this guy? So compute. And the answer is yes, and in fact, this is 0. And we will see why. And so what's the behind the principle? So the motto first is the Kato's balancing Kato's zeta elements still knows these answers. That's the kind of like a philosophy, is the Kato's zeta elements still know the answers. And the main, so how can we do that? So in fact, we use a kind of the analytic incarnation of the Kato's Kolyvagin system. So analytic means like, I don't know. So basically modular symbols. That's what I want to say. And one thing I want to emphasize is that I do not say Euler system, but Kolyvagin systems. So in some sense, I squeeze zeta elements as much as possible and derive something more precisely. And this leads to the so-called the concept of Kurihara numbers, which I will explain later. In fact, Kurihara himself found these numbers in a completely different way. And so I will use the notation like a delta tilde underline. It is the collection of the whole Kolyvagin. Kurihara numbers, something like that. And where does it come from? Is the so from now on I will like define all this thing, and it looks like too random. And let me just write down the one line. This is the image of the Kato's Kolyvagin system under the dual exponential map. So the Kato's Kolyvagin system and the dual exponential map, then this number appears. That's the kind of motivation for me. So then let me define what the Kurihara numbers are. So let me recall the modular symbols. It's a very standard one. So E over Q is an elliptic curve. P is the prime, not 2, not 3. And the residual representation is surjective. And the Manning constant is prime to P. Is prime to P, which means I also concern the additive reduction. And F is a modular form corresponding to this elliptic curve. Let's wait to new form. It's gamma not n. curve due to the Broglie-Conrad-Diamond-Taylor. And for a rational number A or B, then the plus symbol is defined by the following equality. It's the 2 pi integration from 0 to infinity f of ab plus iy dy is the plus symbol times the plus Néron period plus the minus symbol times the minus Néron period. And because of the surjectivity condition and Manning constant assumption, it is always p integral. The plus symbol is the always p integral, so we can take the mod p reduction later. So these are standard things. And let me recall the Kolyvagin primes. Let me fix the prime k. Let me fix an integer k, and script pk is the set of primes, and L doesn't divide NP, and L is congruent to 1 modulo p to the k, and AL is congruent to L plus 1 modulo p to the k. And for each prime in pk, let me fix the primitive root eta L modulo L. And using this primitive root, let me define the discrete log eta LA lies in the z modulo L minus 1z by the eta L to this log is congruent to A modulo L, standard thing. And Mathcal NK is set of all square-free products of the primes in PK. The primes in PK, and for each n in NK, I define the ideal IN lies in ZP is generated by the L minus 1 and 1 minus AL plus L, and L runs over all the divisors of n. Okay, now we are ready to define the three higher numbers, and for n, the square-free product of Kolyvagin primes, and let me just n1 because it's the largest thing, the largest set. And delta n tilde is defined as follows. So sum runs over z mod nz cross, and let me take the plus symbol here, times product L dividing n and discrete log eta LA. Of course, it does not make sense, and I'll take all these numbers like a mod IN reduction. So this number lies in the ZP modulo IN ZP, where on overline is the mod IN reduction. And because we chose like a many primitive roots, so this number itself is not well defined, but its valuation is well defined, which means like this one is well defined up to units. and this is natural because when we consider the Kolyvagin derivative, we fix all the generators of the group ring. That this is the same thing indeed. ZP modulo I and ZP cross. And of course, if we put n equals 1, then it recovers just L value. This is just zero symbol, which means just the L value divided by the Theorem period. And on the line.
Sorry, Sanho, can I ask a question?
Sure.
What is B in your definition?
Oh, where is B?
Yeah, what is B in your definition? In your Kolyvagin number.
Sorry. This
B.
is N. Yeah. What am I thinking?
Okay.
Sorry about that. Yeah. Maybe I was confused when I defined the plus symbol. Yeah, it's just A over N.
Okay.
Yeah,
This is N. Okay.
Sorry about that.
That's fine.
Yeah. Thank you very much. Okay. Okay, so these are the whole collection. The collection of the Kurihara numbers. And because when we put n equals 1, we recover the L value. So this is kind of the discrete variation of the L value in some sense. Discrete variation of L value. So I mean, this is a kind of, comparing with the other a periodic function or L value. So if I let me just comparing with the other analytic stuff, analytic objects. So if I have the Kato's Euler system over a cyclotomic ZP extension, then Kalman map gives me the periodic functions. And if I just do Kato's Euler system over Q, and the dual exponential map gives me the L value. And this is just kind of cyclotomic deformation. And using the derivative process, we obtain the Kato's Kolyvagin system. In fact, here, the dual exponential map, which we need to refine a bit because the Kato's Kolyvagin system lies in the torsion coefficient. So it's the in fact, what we need is a torsion coefficient version of the dual exponential map. Then we obtain the Kurihara numbers. So, and this also appears, in fact, also appears in refined Iwasawa theory. Visible the following Kurihara. And okay, so using this number, what can we do? And in order to apply the language of the Kolyvagin system, and let me recall what kind of numerical invariants are associated to these numbers. Am I too fast? Sorry. Let me slow it down a bit. Numerical invariant associate to the collection of the whole Kolyvagin numbers, and this is called the vanishing order. Sorry, before doing that, so I should define what nu n means. Nu n is the number of prime divisors of n. And this is the minimal number of nu n such that delta n tilde is non-zero. This is called the vanishing order. And round zero is nothing but the valuation of the L value. And for each delta n, we can define the periodic valuation as follows. It's the maximal J such that delta n tilde lies in P to the J ZP modulo I n ZP. And we fix nu n and collect all such delta n and take the minimal one. That's the round I. It's a minimal valuation of whole delta n with the fixed number of prime divisors. So nu n is fixed by I. And collect all the delta n without fixing this I, and just consider the minimal valuation, then is round infinity delta on the line is the minimal valuation of the whole round delta n. I is bigger than or equal to 0. So these are whole numerical invariants I need to describe the Selmer groups. Any question up to now? Okay, let me continue. So the first main theorem is as follows.
And who?
Yes. Sure.
I was just wondering, when you were defining the set, sorry, maybe this is going back a few pages. When you define this set Pn or Pk, is it immediate to see that set would be non-empty?
Yes. These are infinitely many. It's using capital density.
So even though your residual GAVA representation could be whatever, you can still find infinitely many primes AL that's looks like.
I assume the residual representation is surjective, and
yeah, I was just wondering because this AL is congruent to L+1, looks like some Eisenstein thing, but we can still find.
There are many such things. Yeah.
And maybe another elementary question. So you had this map from this Kolyvagin system to Kurihara numbers.
Yes.
I was just wondering what the domain and codomain of that map is.
Oh, so yes, that's a good question. And so here, so in order to do that, so it's a little bit delicate because before taking the so let me briefly explain here. So let me say a Z Q zeta n is the Kato's Euler system, not Kolyvagin system, and take the Kolyvagin derivative dn zq zeta n Kato, and compute. So this one lies in the characteristic 0 thing, and take the dual exponential. And we need to more careful because we need to compute, in fact, the integral image in order to measure valuation stuff. And this one is the some constant times delta. I mean, not delta n, like some like a modular symbol. Sorry, some complicated modular symbol thing. The symbols, and taking the mod ion reduction. It's a very lot of things. It's some delicate things are come in, but like this is a brief thing. So then this one recovers the Kato's Kolyvagin system, and taking mod ion reduction, it recovers the sum number times delta n, something like that. That's how we make the connection. And yeah,
I see. So the n comes from the fact that you're looking at this Kato element in Q zeta n.
yes.
Okay. Thank you.
Yes. Very much for the question. And so E over Q, P is the larger than 3, residual representation is surjective, and P does not divide the Riemann constant, and I do not assume any like a ordinary supersingular such thing. And the followings are equivalent. And the vanishing order of the collection of Kurihara number is finite, which means the whole collection of Kurihara number is the non-trivial, is equivalent to Kato's Kolyvagin system itself is also non-trivial. So this one can be regarded as a kind of cyclotomic version of the Kolyvagin conjecture. Cyclotomic version of Kolyvagin conjecture. And the third is, this is equivalent to a very small part of the Kato's Iwasawa main conjecture. Indeed. Kato's Iwasawa main conjecture, only at the augmentation ideal. Ideal holds, which means, of course, the formulation is already appeared in the scene one's talk, so let me just briefly recall what it means. Let me just write down the statement. The first Iwasawa cohomology Qt is the Tate module of the elliptic curve, and Z Kato over Q infinity, quotient by that. And the other side, I have the characteristic ideal of the dual fine Selmer group. And I do not need the whole part. I only need the order at the x lambda. That's enough. And all these three statements are equivalent. And remark. And the first statement allows us to have the structure theorem of the Selmer groups. In terms of delta. Okay, this is the main part of this, the second part of this talk, second theorem. And the second one implies the non-triviality of the Kato's Kolyvagin system, implies a structure theorem of the p-strict Selmer group, cell 0, in terms of the Kolyvagin system, the valuations of Kolyvagin system, Kato's Kolyvagin system. And this is, in fact, already done in the Major Rubin's Kolyvagin system book. And the third, what I want to emphasize is this is strictly weaker than the Iwasawa main conjecture. In particular, I do not need any mu invariant type. I can completely ignore the mu part of the Iwasawa main conjecture. Then IMC. And in fact, another remark is in fact, the same argument exactly works for the Higginbotham point setting. So using that, so then the Kolyvagin conjecture is strictly weaker than the Higginbotham point main conjecture. So these are kind of implications of this theorem. And one corollary, under the same assumptions, and delta tilde underlined is non-trivial if one of the following holds. First, he has good ordinary reduction at P. Good ordinary at P, because in this case, we know the USL main conjecture inverting P at least. So Kato, Skinner-Urban, and 1. And of course, this good ordinary reduction will removed after the Castelli 1 and the Fouquet 1. Yes. And they are, after they publish, then this kind of thing will be removed. And even without this kind of USL main conjecture, and in fact, if analytic rank is 0, then Kato's explicit reciprocity law already implies this Kolyvagin system. Sorry, is a delta tilde underline is non-trivial, especially delta 1 is non-zero. So it is free. It does not use any USL main conjecture or 3. And in this case, analytic rank is 1, and you have semi-stable reduction of P. And this is due to the recent proof of the parallel conjecture due to Botany-Damong-Benerzi and Burungale Skinner Tian. Burungale Skinner Tian. Yes. So in particular, in 2 and 3, I do not use any USL main conjecture. And this non-triviality implies the following theorem. This is now I can describe the structure of Selmer groups.
Hello, Chanho, there is a
yes.
question in the chat.
Sorry. Yes. First thing is how the first statement shows the structure of Selmer. That's exactly what I'm now writing. Thank you. So keep the same assumption. So F, the vanishing order is finite. Then first, we know the Selmer rank. This is nothing but this vanishing order. And the second, we can determine in fact, not all, we can determine the half of the higher fitting ideals, but it's enough because we know because of the Cassel state, the flux generalized Cassel state pairing. So fitting ideal, the ith fitting ideal of the Selmer groups. In fact, now let me take the Pontryagin dual is P to the partial I of delta underlined minus partial infinity. Sorry, it's partial infinity delta tilde ZP for all I larger than or equal to the vanishing order, with I is congruent to this vanishing order, mod 2. But because of causality pairing, 1 and 2 really determines the whole structure. And the third one is just the corollary of this guy. The length, the ZP length of the finite part, the Selmer group, divisible, divided by the maximal divisible submodule, then this is nothing but the partial vanishing order here minus partial infinity this. So this is the structure theorem and the remark. So as I said, the flux generalized causality pairing is essential. Says like a 1 and 2 is enough to determine the whole structure. And comparing with the original Birch-Singleton-Dyer conjecture, and we have the following conjecture. This term, the minimal valuation of the whole Kolyvagin number is equal to the sum of the periodic valuation of the local Tamagawa vectors. In fact, when the analytic rank is 0, this conjecture is equivalent to the P part of BSD formula. Okay, this is the this is the main result. Any question? Okay, then let me make some remarks and sketch the proof. As I said, like the first one is when the L value is non-zero, then the conjecture I said is equivalent to the P part of the BSD formula. And second, and so in my like a structural theorem, this term like really like plays the role of the leading term. And in fact, all I behaves like the ith Taylor coefficient, something like that. Yes, that's how I like feel from this statement. And going back to the example, so back to the examples. So first example regarding the structure of the K-Shaprovich group. In fact, the delta 11 times 41 is non-zero in Z mod 5Z, so which implies the K-Shaprovich, the phi part of K-Shaprovich group should be generally generated by 2 elements. So which means that it should be like a Z-mod 25Z, the 2 copies of Z-mod 25Z. And also in the second example, we compute like a delta 71 times 401 times 631 is non-zero in Z-mod 5Z, which implies the mod 5 Selmer group of this elliptic curve has dimension 3, and we know the rank is 3, so the T-sharp of each group is trivial. The 5 part of the T-sharp of each group is trivial. Okay. Now let me explain how the proof goes. The first statement is rather easy. So delta tilde is non-zero and Kato's Kolyvagin system is non-trivial when Iwasawa conjecture at the augmentation ideal. And this one is done by like making the connection using the dual exponential map. And the converse is also not very hard by considering the concept of corank of the Kolyvagin system. And from the non-triviality of the Kolyvagin system to the augmentation ideal part of the Iwasawa conjecture is completely done in major Rubin. And in fact, if you look at the proof, it turns out that they just did not write down, but like this is an if and only if statement. So this is kind of interesting observation. And the proof of the second part, the structure theorem, is rather like involved. By the way, the Kurihara also obtained the same structure theorem much earlier, but like he needed like many assumptions like mu equals 0 in Iwasawa conjecture, the full Iwasawa conjecture or something like that. And I do not need such a thing. Theorem 2. So the idea start from the structure theorem of major Rubin. And they describe the structure theorem in terms of the Kato's Kolyvagin system. And I know explicit formula from the kappa n to delta n. Sorry, delta n. But okay, how can we go there? Is the cell. This is the problem, and in fact, there is no reason to for example, the structure of Selmer groups and structure of the p-strict Selmer groups, they do not have to determine each other. They are only connected by the exact sequence. But if we consider all the variants of these Selmer groups, then the story becomes slightly different. So apply Bottle-Tate. Not just this one Selmer groups to all so-called the n transverse variants. Then they have more relations. Okay, so these are kind of the starting point. And another unfortunate thing is that delta n tilde satisfies the functional equation. It's a good thing and bad thing. Why I said a bad thing is that half of them must be vanished. Half means in terms of the parity of n. Although the Kato's Kolyvagin system does not vanish. And how to fill this vanishing, and one good thing is the generalized CalTech pairing helps. And now we have like these tools, and as I said, like a cell and cell zero do not determine each other. So at the end, we just consider all the possible cases, but like they are not very different because when we compare them, like a co-kernel is always like a rank 1, so we can like do some case by case verification. And this case by case means like depending on the number of generators in both Selmer groups. These verifications are needed. This is the end of the proof. And before finishing, then another corollary of this theorem is under the same setting, like so for example, like a first one. So I mean the rank 0 p converse follows. It does not use like it's, I mean, not just somewhat like in a different way. And second, and if the Iwasawa main conjecture and X lambda holds, then the p-parity conjecture follows. And I think this one is first observed by Sakamoto, Ryotaro Sakamoto. And if I just compute the random delta n, if I have one non-zero, then I can say, okay, the rank is smaller than or equal to nu n. So this gives upper bound of the rank of the elliptic carbon, sorry, nu n. Okay, so let me draw one diagram and let me finish. So Iwasawa main conjecture implies the p part of BSD formular of the analytic rank is smaller than or equal to 1. This is the kind of the main application of the Iwasawa main conjecture, and I go in a somewhat different way. So first, I just invert P. Let me just write down like a tensor QP, and if good ordinary reduction, this is true. This is the Kato Skinner-Urban 1. And this is, of course, implies Iwasawa main conjecture at the augmentation ideal X lambda. And this is the equivalent to Kato's Kolyvagin system is non-zero, which is also equivalent to delta n tilde is non-trivial. And if E has analytic rank smaller than or equal to 1, then we know the Kato's Kolyvagin system is non-trivial. And from here, the non-triviality of the Kato's Kolyvagin system, we know the structure of the cell zero. This is major Rubin. And finally, this implies the structure of the Selmer group. And so this is the kind of the result coming from the squeezing Kato's oil system as much as possible. And yeah, let me stop here, and thank you very much.
Thank you. Any questions, comments? Can you switch?
Sorry, I am a little confused that what you write. Did you write that the Selmer conjecture implies the P part of BSD when the analytic rank is 1 in the ordinary case?
I mean, like, not so. This is the what I want to say is that this is the kind of main application of that. I did not say any like a specific conditions here, and that's how I like a. So I mean, rank 0. I don't think rank 0 and rank 1s are kind of the. For me, it's kind of the main application of the Selmer conjecture in the
right. But I mean,
yeah.
For example, in the ordinary case, in the rank 1 case, it's I don't know if the Selmer conjecture implies the the upper one.
Upper one, yeah.
I don't know if the Selmer. I know that in the super singular case, the Selmer conjecture does imply the BSD formula in the rank 1 case, but in the ordinary case, I don't seem to. I think that the BSD formula can be deduced from the Selmer conjecture, or maybe I missed something.
I mean, like it's the one. The in direction one thing in mind was the Jachevsky 1 paper in there.
Yeah, but that's a different kind of Selmer conjecture.
I mean, you're right. Yeah, you're right. I mean, but like, yes, you're right. Okay, yeah, okay, yeah, okay, okay, and yeah, I thought, but like yeah, you're right. Yeah, thank you. Yeah.
Chano, so I was just wondering, so these Kurihara numbers delta n determine the structure of the Selmer group over Q.
Yes.
And but you can get these Kurihara numbers from your Kato's zeta elements at Q adjoint zeta n.
Yes.
And so my sort of naive question is, so are we saying that the size of the Selmer group at Q zeta n determines for all these n's, they determine the structure of the Selmer group at Q?
I mean, yes. I mean, structure is determined, then the size. Yeah.
So is that So
I mean, so one thing in mind is the use the whole Kolyvagin system, not just the leading term part. Then we can determine the structure. Yeah.
So is that easy to see? Okay, not easy, but like, can we see that just by using Selmer groups at Q zeta n?
Oh, it's just going with the Q zeta n. You mean the?
Is it possible? Yeah, if I know the size, whatever size means of the Selmer group of Q zeta n, can I know the structure?
One reason I stick to like over Q is I don't want to consider the fitting ideal over non-PID things. I mean, yeah. I mean, like maybe you can deform it, but like I haven't thought about it too much.
Oh no, I just meant if I know if the information given to me is the size of the Selmer group at Q zeta n,
okay.
Only that, and without using this machinery of Euler systems, or Kolyvagin systems, can I deduce the structure of the Selmer group at Q? I
mean, like if you then you don't need the you don't need the information over Q zeta n. I mean, Kato's Kolyvagin system, if it is non-trivial, it already determines the structure of the Selmer groups over Q. Yeah. I mean, so the problem is like even if you know the structure of the Selmer groups over Q zeta n, that doesn't mean the non-triviality of the like a kappa n, for example. That's the kind of different thing.
And so maybe one more question. And so you have all these, so you use this to determine the size of SHA, and are there analogs of Kurihara numbers for class groups?
There are. I mean, like, in fact, I think the one paper of Miho Aoki, she considered, like, for example, the Gaussian Kolyvagin systems determines the structure of the class group. I forgot the plus minus part, but like, yeah, and cyclotomic unit also, she like made similar things to determine the structure of the class groups. Yeah.
Oh, thank you. Thank you.
Any more questions, comments?
Yeah, I have a question. Yeah,
Yes.
Chanho, can this Kurihara number say anything for the fine Selmer? That means your cell zero.
You mean find Selmer groups?
Yeah, the cell zero.
Cell zero, then you should just use the Kolyvagin system itself.
Okay, but I mean, can your Kurihara number, can your cell zero be interpreted in terms of cells, in terms of a Kurihara number? Is there...
I'm not sure, because I mean, so for example, for example, my proof is a kind of the structure of cell zero in terms of Kato's Kolyvagin system is
Okay.
kind of transplant this to the usual Selmer groups, then the Kurihara numbers naturally appears.
Okay.
So yeah, in cell zero is I'm not sure about the direct connection between cell zero and the Kurihara numbers.
I see. I see. Okay.
Any more questions?
These Kurihara numbers seem to be connected with things that we'd like to compute. Are they explicitly computable in practice?
Yes, I mean, as you see, if you just the computation of modular symbols and discrete log and this everything.
Mm-hmm.
So it's real. I mean, yeah. As I said, like these are really like computed by the Sage, for example.
Mm-hmm.
Yeah. So I mean, one interesting thing is, so for example, like you can like check the Iwasawa main conjecture and the augmentation ideal by computing this number. Yeah.
Mm-hmm.
Yeah.
Any more questions? If there is none, let's thank the speaker once again.
Thank you very much.